All right, I just want to quickly run through the basic differences between a series and a parallel circuit because you're going to be having to draw those today. So it's important that you know some of these differences. We will add to the differences as we learn more about current and resistance and whatnot, but for now we're just going to do some basic how to set up and draw these guys. So the first idea would be that if you are in a series circuit, like this one over here, got yourself a power source, you got your wires, and in this case we've got a light bulb and then another light bulb. If you notice, there's actually only one pathway for the electrons to follow. So you're going to start off at the negative terminal, and this is the positive terminal here. And the electrons are going to move, going to have to pass through this light bulb. Then they'll have to pass through this light bulb. So there really is only one pathway for these electrons to follow. Whereas if you go over here to the parallel circuit, when you leave the battery, they could go all the way around in that pathway, or they can take a detour and go through this light bulb. So you can see that there are actually two different pathways for the electrons to travel. That's going to make a difference between what happens with voltage and what happens with the current, but we'll talk about voltage first. So if they are going across the battery like they are in the parallel circuit here, let's say that in my battery, let's say I've got a 12-volt battery, and then let's say that these lights are exactly the same in their voltage. When I go around and I am using, if I'm going and I'm going through the voltage here, this light bulb and this light bulb are going to share that voltage. So if they are the exact same type of light bulb, then they'll use the exact same amount of electricity, and in that case I can expect to split the voltage evenly between them so that this light bulb will be 6 volts and this light bulb will be 6 volts. We would say that this would be VT for total, and we would call this V1 and V2 for the voltages of those particular light bulbs. So then we would say that the total voltage is equal to the voltage of light bulb 1 plus the voltage of light bulb 2, which means we've got 6 volts plus 6 volts. So the total voltage is equal to 12 volts. Now when we look over at the parallel circuit, a little bit of a different story. Now we've got the separate pathways so that each of the light bulbs has its own pathway. So that flow, that current, that electrical pressure is full volume in this circuit and full volume in this circuit. So again, if we had the same battery, the 12-volt battery, we would have 12 volts here, but this would have equal access to the battery that this guy would have. There is no sharing of the voltage. So in this case, in a parallel circuit, we would say that VT, or V total, is equal to V1, which is equal to V2. No sharing. So the total voltage then would be equal to the 12 volts and equal to the 12 volts from each one of those. No sharing of the voltage in those particular ones. Now because of that, I'm going to go back to the series. If I was to add a light bulb into this thing here, you can imagine that putting another light bulb in would mean that I'd have to share the voltage even further for these light bulbs. Okay, so let's say that I did that. Let's draw ourselves that circuit again. So here now we've got a new series circuit, and then we've added a third light bulb in there. We still had originally 12 volts here, but now we've got it shared between 3 equal size light bulbs. So that means that 12 divided by 3, I'd have 4 volts here, 4 volts here, and 4 volts here, so that each of the bulbs will add up to 12. Well, if that's the case, then each of the bulbs are going to be dimmer. Dimmer because there's less voltage available to actually light up that particular light bulb. So again, if you have a look at the top here, we've got one battery with 2 light bulbs, so we can have 6 volts each, but we only have one battery here, and each of the 3 light bulbs can only have 4 volts. 6 volts is a lot brighter than 4 volts. Okay, so that's why adding more lights you're going to get dimmer because of the shared voltage between all of those lights. In the parallel circuit, we've added a third light bulb. So here we started off with our 12 volts, but this guy has its own pathway, so it's going to have full 12 volts. This guy has its own pathway, so it's got full 12 volts. And then the third light bulb has its own pathway, so it's going to get the full 12 volts as well. There's no sharing. When you have a parallel circuit, the total voltage is the same for every branch in the pathway. Now that would be a little bit different if we had a combination circuit. Let's say that somewhere along this pathway here, let's say I added a light bulb. Well, in that case, then I would have some shared pathway. So this guy would still have its own path, that's 12 volts. This one would have its own path, 12 volts. But in the last pathway, there's two light bulbs sharing the voltage, so they would be 6 each. So you would expect then that for these bulbs here, these guys would have full brightness, and then these guys would be dim. Okay, and again, that's because these guys are in a perfectly parallel pathway to the battery, whereas these two light bulbs, while they are in parallel to this guy and this guy, they are in their own series circuit. So they will share. When you're in series, you share. When you are in parallel, you have full voltage, therefore full brightness and full access to the electricity. So now let's chat about current. Now, if you were to actually measure the current, which again we'll talk about in more detail in a different lesson so you have a better understanding of what it is. It's basically the flow, the actual physical flow of those electrons. It's going to be the same at every single point in the circuit. So if I was to measure in this part of the wire right here, I would get the exact same reading as I get here, as I get here, as I get here. It would all be the exact same. And I would do that, measure that, using something called an ammeter. And you actually need to put the ammeter into the circuit. So you can put an ammeter there. You could do it over here at a separate time. I can measure over here, and I could measure over here. It doesn't matter what part of the wire. Make sure that your ammeters are added in series because you want to measure the current that's flowing through that wire. Okay, so must be in the pathway. So you would take a connection, you'd break that wire there, and you put it on the other side of the ammeter. Okay. What would you see? Well, if we're talking in terms of the numbers that you'd see, let's say that we started off with 3 amps for the value of our battery. Okay, and we knew that because when we used this ammeter, it tested as 3 amps. When we use this ammeter, it tested as 3 amps. Okay. When we tested over here, it was also 3 amps. When we tested over here, it was also 3 amps because it is the same at every point in the circuit if it's a series circuit. Now when we go over here and we're looking at a parallel circuit, when the energy goes out and it goes to this unique branch, we're going to get a different reading because as the electrons are flowing, keep in mind that current is a measure of the charge moving past a point in a second. When the current is flowing here, it has to divide and go down the two branches. So some of the electrons will take this pathway, and then the rest will continue this way. Then I'll lose some more as they split down that pathway, and so on. So that the current itself flows down different pathways. It will get divided. So the current that I'm going to measure, let's just put my ammeters in quickly. If I put an ammeter in here versus an ammeter in this unique path, in this unique path, and in this unique path, or even in this path over here. So now if I was to take the measured readings of the amperes in each of the sections of this particular circuit, if I had 3 amps here at flowing out of the battery, coming out of the battery here, then when it hits this section here and it can branch, the current can either flow in this direction towards this light bulb, or continue on towards this light bulb, or even continue on towards this light bulb. So that when I actually measure the current that is flowing through this portion, okay, I may only actually get 1 amp rather than the full 3. Same thing over here. If the light bulbs are the same, they'll use the same amount of current because they've got their own unique needs. Now when it comes all back together again, if I was to measure here again, because I've got this guy, and this guy flowing back together again, I'm going to have 3 amps on the way back into the battery. 3 amps coming out but being split between the 3 lights and then flowing back in together for complete current on the way back. If you want another way to visualize this, you could think about it as water flowing through a bunch of different tributaries or rivers. Let me show you. So here we have an example of the current flowing. Let's say that our source, let's say that each one of these little pathways here, the different colors, represent a different amp. So it's all coming out of our original power source, but we've got 3 different pathways for the current to flow. Okay, I hope you can see right away that if I was to measure anywhere near the source in this first pathway here along the source, you can see that it's 3 wide. So in our little symbol case, we're saying that this is 3 amps at this particular location, 3 amps if I measured over here. But if I was to measure in this location, there would only be 1 amp. This location is 1 amp, this location is 1 amp, or if I measured on the other side of the load, it would only be 1 amp, because in this entire outside circuit, there is only 1 amp available and flowing through it. Okay, but when you come back together now in this section, now you've got this guy plus this guy. I've got a 2 amp service, and then over here I've got myself back to being a 3 amp service as I head back towards the battery. So the current in each branch, really important you memorize this, the current in each branch is less than the current through the power source, because the current gets shared between each of the loads, because each load is using part of that current to run its little machinery, whatever it's going to be, whether it's going to be a light bulb or whether it's going to be a motor or whatever. Just as a final thought, you're going to see that the loads that we've just been discussing are going to resist electron flow, and that those charges are going to lose energy. But the current that is before the load, there's the load using the current, will be exactly the same as the current after the load. So when we're measuring current here in this pathway or here in this pathway, we should still get the exact same current reading on either side. And just a reminder that the resistor symbol for circuits will be these mountain peaks. You can draw it with a single mountain peak in the middle, or 2 mountain peaks in the middle, or 3 or 4, it doesn't really matter, but at least 1 or 2 in the middle is a good plan for your resistor symbol. And this is just showing that a resistor is considered a load, that the load is slowing down the current pathway. Welcome to your lesson on drawing circuits. I'll try to get into it and go through it as quickly as we can. First of all, I'd like to introduce just a couple of new symbols that you haven't seen before. The first one would be the fuse up here at the top. The fuse is a little tiny thin piece of metal, and we draw it like a little squiggly here. Up first, then down, please. And basically what this does is, if the circuit begins to heat up because there's too much electricity in the wire, then the wires are going to possibly melt. And you don't want to either melt the wires and cause a fire in the house, or to damage one of your loads, whether it be a motor or a light bulb or whatever it is that's on there. You don't want to damage it. So what will happen is if the wires do begin to heat up, this little thin piece of metal will actually melt. It's designed to melt so that if this piece of wire and this piece of wire gets too hot and sending heat through there, when it melts, it breaks the circuit. And if it breaks the circuit, it saves the light bulb or the motor or whatever else you've got on there. It saves them from being damaged by too much current. So fuses are very important for safety. You guys have fuses in your house. Literally every safety panel in your house will have some kind of version of a fuse. Now in your house, you might have the little glass fuses like I do in my house, or you might have a complete circuit breaker which can be reset and reused. Fuses can only be used one time and they have to be tossed, but a circuit breaker is much nicer. We use this symbol though for fuses to show that there's a safety fuse in the wire. The other one that you haven't seen before is called a ground connection. Basically you just have the wire going into ground. That's basically what it shows. We're not going to do any pictures that actually need to use this. I just wanted to show you what it looked like. 2 other things, an ammeter, which we started talking about when we talked about current, and a voltmeter, which is how we measure the potential difference in the wire. And we'll get into more about how to measure ammeters and how to calculate the amperage, and the same thing with the volts, how to calculate the number of volts and all kind of stuff, but that's for another lesson. Let's get into drawing these guys. So please make sure you're using a pencil. It's always nice to use a pencil because if you make a mistake, it's easier to fix. So please make sure you're using a pencil. Ruler, if you aren't too neat with your lines, then yeah, grab a ruler. If not, I'll still accept things without a ruler, but it is good practice. I can't use a ruler because I'm doing this on an iPad, so it'll just have to be what it'll be. And then of course you want to demonstrate that you can draw the correct symbols. You choose the right symbols to draw the circuits. Okay, so the simple circuit, anytime you see simple circuit, what they mean is that this circuit is in series. In series means that there's only one pathway, and any load or switch or anything like that must be on the same pathway. Now in this case, we've got one load and it's controlled by a switch. So if it just says load, you can choose what load you want, whether you want it to be a light bulb or a motor or whatever. I'll probably just do a motor. So it's one load that is controlled by a switch. Keep in mind, you need to always have a power source. I can do a single cell, I can do a double cell, I can do a triple cell. The more cells I add, the more power I have for my devices. One load that's controlled by a switch, so I don't know why I always just like to go clockwise. And I usually draw my switches like that. And then there's one load, so I'll just put the load down here. There's my motor. And then I combine it and draw it like that. Number 2, which is down here. So we've got 2 light bulbs sharing the electricity. That means it's in a series circuit, and it's a double cell battery. So I need to make sure I draw at least 2 cells. And the circuit is always on. So there's no switch. I don't need to worry about a switch for this one. Double cell battery, again, I always like to start with the power. 2 light bulbs. So I like to draw the circles first. Then I like to draw the wires, and when I get up to the light bulb, I draw the little light bulb L. And then I can complete the circuit. I always go back and make sure that I read it again. So I've got my double cell battery, check. I've got my 2 light bulbs, check, check. And the circuit is always on. Yep, there's no switch or anything. I'm good to go, I'm done. Next one, number 3. So 3 light bulbs and a power source. 3 light bulbs and a power source. Okay, we got 2 bulbs that are dim. That tells me that they must be in series to one another because they're sharing the electricity. And then one has full brightness, which means it must be in parallel because it has its own path to the battery. It's getting full access to the battery. So I'm going to need what's called a combination circuit. Let's draw this one. So we need a power source. Let's make it a triple cell just for fun. 1, 2, 3. 2 are dim, so I know that they are in a shared pathway. And 1 is full brightness, so it must be in its own pathway. It doesn't say anything about a switch, so I'm not going to worry about it. I always go to the outside one first when I'm drawing these lines. That way I don't have to worry about lines being broken. So let's check it one more time and make sure that it makes sense. We've got 3 bulbs, check. A power source, check. 2 bulbs are dim, those are those 2. And 1 is full brightness, that's that one. I'm done. On to the next one. 2 light bulbs with equal brightness. That means that they must have equal access to the battery. That can be controlled by separate switches. So I must have one switch for each light bulb on its separate pathway. I'm going to need a parallel circuit to do this. Now, this is where switches get a little bit trickier. You have to make sure that they are only in the unique branch. So let's draw our power first. Let's just do a single cell this time. That means I'm going to have a light bulb and another light bulb. Okay. I'm going to have a switch in this light bulb's pathway. And I'm going to have a switch in this light bulb's pathway. Now, here's the thing. This is the correct answer here. I'm going to draw in a different color what would be the wrong answer. If I was to put a switch here in the pathway, okay, this switch, because of the way that the path is developed, if the electricity comes out of here and goes through, it'll go through that switch before it reaches that branch and before it reaches that branch. So putting a switch here is going to control the entire circuit. So it's important that when you put in the switches, that you want to put them in the unique pathway right here so that it only controls this pathway, and then this switch only controls this branch. Okay, that way this light can be on and this light can be on at the same time. All right, next question. The hall light in your friend's house can be controlled by 2 switches. Well, if it's one light being controlled by 2 different switches, it means those switches have to be on the same pathway as the light bulb. All 3 are on the same pathway. That makes it a series. Okay, so 1 at each end of the hall. How do you do your diagram? Well, it's simple. This is actually easier than it sounds. Power source, a switch at one end of the hall, and I've got a switch at the other end of the hall. And both switches are going to control the same light bulb. Done. 2 switches, 1 light bulb. Finito. Let's do the next one together. So now you've got a closed parallel circuit. That means that our switch has to be closed this time. Got a single dry cell. That's easy. One of the motors can be turned on or off. Okay, so there must be a switch in that motor's pathway. And then two motors are always turned on. So there's no switch in that pathway. We're going to need a parallel circuit. One way to interpret this one is to say that the first motor has its own pathway and the other two motors share a pathway. So it could be a combination circuit, or all three motors have their own pathway and I just don't have any switches. So I'm going to draw both of those for you. So first of all, we draw our single dry cell. I know that this motor needs to have its own switch and it is a completed circuit, so I know the switch is closed. Okay. Then I could have each motor on its own pathway. This is where a ruler comes in handy, but I don't have one. Okay, so that's one interpretation of it. You can see that we've got our one motor, so one of the motors turned on and off, one motor turned on and off, and then two motors that are always turned on. There's no switch in these unique pathways here, so it's always on. And then the other way I can interpret it is I have my dry cell and I have my motor with its switch, and again make sure it's completed, but then perhaps these two motors are actually on the same branch, and both of these would get you correct answers because they aren't explicit about where those two motors are. So both of those are perfectly good answers for this particular question. Okay, next question. Two motors, two light bulbs, and a power source. We're getting fancy here. There's a fuse. That's important. Notice that it says it protects the entire circuit. That means that that fuse has to be in the common pathway for all of these. Just put it next to the power source. That's the easiest way, so that the power has to go through that fuse before it ever reaches any of these loads. Okay. The light bulbs are controlled separately from the motors. When you unscrew one light bulb, the other light bulb will also go out. That's how I know they're in series. And the motors are going to stay on. So give the lights their own pathway, give the motors a different pathway, and then there's no switch. It's just that when the light bulb gets unscrewed, so there's no switch mentioned. Okay, so going to need combination circuit. Okay, we're going to do our fuse. This is the new symbol I showed you at the beginning. You go up, down, and then back to level. So make sure you do a nice little S-bend curve like that. So there's our fuse protecting the whole thing. Then you have your light bulbs controlled separately from the motors, and the light bulbs are in series to each other. So draw my two light bulbs here in series to each other. And then I've got my motors. So again, the motors can do the same thing that we did in the question before. The motors could be on separate paths, or we could have, make sure we put our fuse back in, up, down, up. We could have the two lights being in series, and then the two motors could also be in series to each other. They are not explicit enough in this question for us to know for sure how the motors are actually wired. We just know for sure how the lights are wired. Okay, so both of those are equally great. You just need to make sure that these motors have to be separate from the lights. So whether they're separate but together from the lights, or whether they're separate from each other, doesn't really matter. Both of these are correct. Okay. One final question for practice, more of a thought question. Christmas lights being put up at your house, and you notice one of the bulbs does not work when the rest of them do. Is it wired in series or parallel? Well, I hope you know already that it must be wired in parallel, because if the one bulb has gone out, the other bulbs all still work. So they must have their own pathway to the power. Since the other bulbs have their own pathway to the power source, this must be wired in parallel. All right. Now, if you guys could continue on, you're going to be completing these questions here. If you could make sure that once you finished drawing them all, if you could take a quick picture of your work, make sure you label them 1, 2, 3, 4, 5, 6 so I know what you're doing, and make sure you put your name on your picture, please, so I can tell. Please be very neat. This is where using a ruler and a pencil would be a great idea. and get a picture of that and send it to me on the Google Classroom, and you are done. There will be a couple other little booklet worksheets attached to this lesson. You just need to make sure you get those ones done as well. All right, let me know if you have any questions.